Okay, now we move to talk about a new chapter describing data numerical measures. Now, as you can see in this chapter, we're going to discuss two types of measures, which are measures of locations, and we're going to study the different types of measure of locations and measures of dispersions. Also, we're going to study different measures of dispersion. Now, as you can see, this chapter is concerned with two numerical ways of describing quantitative variables. You know that, remember that quantitative variables are the ones that are stated numerically. Measures of location and measures of dispersion. Measures of locations are often referred to as averages. So measures of locations have different names, have different names, averages. The goal of a measure of location is to pinpoint the center of a distribution of data. Okay? In addition to measures of location, we should consider the dispersion or variation or spread in the data. Now, let's see exactly why the measures of dispersions are important. In other words, if you compare different sets of data using only measures of locations, using only central values, you're gonna draw wrong conclusions. In addition, you should consider, measures of dispersions. To see why measures of dispersions are important, let's give an example. Suppose the average annual salary of physicians is $50,000. So you have two, industries, the physician industry and the computer scientist industry. The average annual salary of physicians is $50,000, and the average annual salaries of computer scientists is also $50,000. So if you look, you will see that if you look at the averages, you will see that the distribution of the two salaries are the same. But you should consider the dispersion or spread of the distribution of salaries. If we look at the salary ranges in the computer scientist industry and in the physician industry, you will notice that even though they have equal averages, even though the two distributions have equal averages, however, the dispersions are different. For instance, if we look at the salary ranges in the computer scientist industry, we see that the salaries range from 20,000, let's say, to 80,000. From 20,000 to 80,000. However, the salary ranges in the physician industry the salary ranges from 40,000 to 60,000. 40,000 to 60,000. So as you can see, even though the two distributions have equal averages, however, the dispersions, we have much more dispersions in the computer scientist salaries than in the physician distributions. So let's see why we have to investigate the dispersions, the measure of dispersions, whenever we want to come up with the right, conclusions. As we saw in this example, just focusing upon the measures of locations, you might come up with the wrong conclusions. So here, measures of location, there are many measures of locations. Here we will consider 5 measures. Basically, namely, are the arithmetic mean, the weighted mean, the median, the mode, and the geometric mean. So these are the ones that we're going to study in these chapters. And these are measures of locations. We study the mean as both a population parameter and a sample statistic. Remember that any characteristics of the population is parameter, is referred to as a parameter. And any characteristics of a sample is referred to as statistic. So here we're going to study the population mean and the sample mean. Okay? Now, measures of dispersions, here we study the range, the variance, and the standard deviation. These are measures of the dispersions. Okay? Sometimes are called the spread or variation. Measure of dispersions or spread or measures of variation. Same thing. Now, measures of location, the population mean. As you can see, this is the formula for the population mean. All we have to do, we sum all the values in the population over the number of values in the population. Instead of writing out in words the full directions for computing the population mean or any other measure, it is more convenient to use symbols. So instead of every time writing the population mean, the sum of all values, we can use certain symbols or notations, and that will make it easier and faster to write the formula. And so here the population mean is going to be represented by this formula. Mu is equal summation of xi over n, where this symbol mu, okay, it's a Greek lowercase letter, is called mu, and that represents the population mean. So the population mean is represented by the Greek lowercase letter, which is called mu, as you can see. It's written like this. And here, this sigma is, of course, the Greek capital letter, sigma, and indicates the operation of summing, okay, the operation of adding, okay? And so this, the lowercase Greek letter mu, of course, it will stands for the population mean, and then n is the number of values in the population. The population might have 50 numbers or 60 numbers or 60 values. Then it is n, stands for the number of values in the population. X represents any particular value. So here, summation of xi, all x is represent a particular value in the population, and this, of course, sigma is the Greek capital letter and indicates the operation of summing, and you put this, notation to indicate the population mean. Remember that any measurable characteristic of a population is called parameter. Any measurable measure of the, any measurable characteristic of the population, is called, a parameter. Therefore, the mean of the population is a parameter. It's an example of a parameter. Okay? Same thing, the standard deviation of the population or the variance of the population are, parameter, are examples of a parameter. The sample mean, of course, it is the mean of a subset of the population. Okay? For raw data, ungroup data, the sample mean is given by the following formula. This is the formula of the sample mean. Using the shorthand notation x bar, of course, the sample mean is stated as follows. Sample mean, x bar. So we're going to, refer to the sample mean by writing x bar. X bar stands for the sample mean, which is equal the summation of x, okay, over n, where x bar represents the sample mean. It is read x bar. N is the number of values in the sample, and x represents any particular value in the sample, where sigma x represents the sum of the x values in the sample. Okay, so sigma x stands for the summation of the values in the sample, if we're talking about the sample, and also sigma xi, of course, represent the summation of the values in the population if we are talking about the population. Okay, let's give some illustrations, some examples of population mean and sample mean. Remember, population considers all values or observations in the data. However, a sample considers a portion of the population. Example or illustration or example number one, it says we have 15 famous boxers in Lebanon, and here they are listed the weights of these famous boxers in kilogram, those in Lebanon. So we have 15 famous boxers in Lebanon, and here we are listing the weights of these boxers. As you can see, those are the weights of these 15 boxers in Lebanon. So why is this information a population? What is the mean of the weights? Why you think this is the population? Because we are, considering all the famous boxers in Lebanon. That's why it's a population. We are not considering a portion of the famous boxers in Lebanon. We are considering all boxers, all famous boxers. That's why we have a population. Now, what is the mean of the weights? Of course, we use the formula. This is the formula. We use, since it is a population, we use the mu. Mu, of course, is used to represent the mean or the average of the population. So, which is summation of all values over the number of observation in the data in the population. And we put all these values, as you can see, okay, we sum all of them over 15. We have 15 weights. We divide by the number of, this is n, represent the number of observations in the data or in the population, and we come up with 83.8. This is the average weight in the population. Now, remember, every characteristics of the population is a parameter. Okay? Every characteristic of the population is called a parameter. Now, the second question, the annual incomes of a sample of physicians at Beirut Hospital. So Beirut Hospital has certain number of physicians. And we are talking about the annual incomes of a sample of those physicians. Perhaps in Beirut Hospital there are 100 physicians, so we took a sample of those 100 physicians. So here we are talking about this sample. These are the incomes of a sample of physicians in Beirut Hospital. We have how many incomes? 1, 2, 3, 4, 5, 6. So we just took 6 incomes of 6 physicians in Beirut Hospital. So we're going to find what? Give the formula for the sample mean. This is the formula. We don't use the mu. For as far as the sample is concerned, we use, to find the mean or the average, we use X bar. This is X bar. It is used to represent the sample of the mean of the sample, which is equal to the summation of X over N. That is, we sum all the items, all the, here in this case we have incomes. We sum all the incomes of the sample and we divide by the number of, the data that is used, which is here now 6. So we sum them, we come up with 51,000. This is the sample mean or the sample average. Now, is the mean you computed in B here, the mean, a statistic or a parameter? Remember, any characteristics of the population is a parameter. And any characteristics of the sample is a statistic. So statistics is a characteristics that is used for the sample. And the parameter is a characteristic that is used for, the population. What is your best estimate of the population mean? Remember, the best estimate of the population mean, since we are talking about a sample here, so the best estimate of the population mean is the sample mean. And the sample mean we calculate is 51,000. Therefore, 51,000 is used to represent the population mean. This is the best estimate of the population mean, is the sample mean. Okay? Now properties of the arithmetic mean, whether it is population mean or sample mean. Of course, every set of interval or ratio level data has a mean. Remember, talking about here interval or ratio level, those are related to the quantitative data. Therefore, such as ages, incomes, weights, and so on and so forth, you can have mean for these because they are stated numerically. So you can find the mean of those, as we did over here. Second characteristic of the mean, all the values are included in computing the mean. All the values are included when you compute the mean. Here, let me just stop here for a second to talk about a weakness of the mean. The mean has some weakness. What is that weakness? What is that weakness? The weakness is that because in the computation of the mean, every value of the item is used to calculate the mean. That is, all values are used in the calculation of the mean. Now the question is that if one or two values are either extremely large or extremely low compared to the rest of the data, then the mean you calculate will give you an average that is not at all representative of the data. Let me illustrate what I'm talking about. Say, for instance, here, say we have the following values, okay, 5, 6, 8, 10, and 100, okay, 100, and I'm telling you, calculate, you have 1, 2, 3, 4, 5 items, and I need to calculate the mean, the average of these 5 items. Remember, all these items are more or less close to each other. Very, as you can see, very close. The values are very close to each other. However, there is one value that is extremely large. Extremely large. So when I calculate the mean of these, we come up with this mean. Now, of course, let's say this is a sample. A sample that consists of 5 numbers. So to calculate the mean, what you do, I get x bar is equal summation of x over n. We're going to come up with 5 plus 6 plus 8 plus 10 plus 100 over 5. And you're going to come up with a value of the mean. It's going to give you a value, the mean of this will give you a value of the average that is not representative of the data at all. So if you count this one here, you're going to come up, 118, 20, 23, 129. 129 over 5. 129 over 5, you're going to come up with a very large number. It's not going to be perhaps over 20. over, the average is going to be a value over 25. Over 25. So you're going to have a value above the 25. Now, this value, which represents the average of the data, is not representative of this data. This data you're talking about 5, 6, 8, 10. This is 25. So this will give you an average that is not at all representative of the data. That's why we are saying that the mean has some weakness. And that is when you have one or two values that are either extremely large or extremely low compared to the rest of the data, then you're going to come up with a value of the mean that is not at all representative of the data. This is the weakness of the mean. Now, the mean also is unique. It's unique, that is, there is only one mean in a set of data. Yes, we have one mean of a set of data. Now, the sum of the deviation of each value from the mean is 0. So, whenever you take the summation of each value, the summation of the deviation of each value from the mean of the data, you're going to come up with 0. As you can see this example, you have, for instance, these values, okay, 4, 6, 9, 5. And what we do here, we calculate the mean. The mean is going to be what? 6, okay? Now, if I get the deviation, the sum of the deviation of each value from the mean, you're going to come up with 0. Take the deviation, summation, x minus x bar is going to be equal 4 minus 6 plus 6 minus 6 plus 9 minus 6 plus 5 minus 6. You add them, you come up with 0. This is a very important rule about this. The sum of the deviations of each value from the mean is going to equal 0. It's going to give you a value of 0. Now, we move to the weighted mean. Remember that the weighted mean is a special case of the arithmetic mean, whether the sample or the population mean. Okay? Now, that weighted mean, of course, it occurs, of course, when there are several observations of the same value. When you have several observations of the same value, then it's better to use the weighted mean to calculate the mean instead of using the arithmetic mean. It will be easier to use in that case when you have several observations of the same value. It is easier to use the weighted mean than using the arithmetic mean, that is the sample or the population mean. So what is the arithmetic mean? Of course, let's give you just an example over here. Let's say, for instance, in August, an investor bought 200 shares of Microsoft stock at 100 per share. 200 shares, and each share is priced at $100 per share. $1 per share, and I bought 200 shares. In October, the investor bought additional what? 500 shares of $60 per share. So you have 500 shares, and each share, costs $60. So this is what? This means what? There are many observations of the same value. 500 shares, the same value, which is what? $60. Now, in December, he bought an additional 500 shares at $55 per share. So you're going to have 500 additional shares, and each share is priced at what? $55. So you have what? Several observations, of the same value. So if I'm going to use the mean of these, what is the mean? If let's say, what is the weighted mean price per share? I could use the regular way, which is calculating the mean, the average mean. What you do? What I'll do? I will do, 500. It's going to be long, very long, very, very long. I'm going to say, 500, and each one is 55. 55 plus 55 plus 55 plus 55. How many? 500 times plus. You're going to have what here? 200. 200 at what? At 100. You're going to say 100 plus 100 plus 100. And you're going to have a very, a long way and lengthy, of course, to calculate the mean. So an easier way is to use the weighted mean. The weighted mean is this is the formula here, as you see. X bar sub W. W weights, okay? X bar sub W, which is equal what? W1 X1. This is where W is the weight. Okay, W1 X1 plus W2 X2 all the way. And we're gonna have this summation WX. W is the weight. Weight, of course, this is, of course, the weight, okay? Which is, weights are the frequency counts. Weights represent or stands for the frequency counts, okay? So the weights times X over the summation of the weights, as you can see over here. Now, where W are weights, which are frequency counts. Now, what you do here, so X bar sub W is going to be equal 200. These are the weights. The weights, this frequency counts. How many, how many observations are counted here? 200 with the same price. So it's going to be 200 times what? Times X, the X 100 plus 500 times 60 plus 500 times 55 over the sum of the weights. What the weights? We get 200. What here? We get what? 200 plus 500 plus 500. And we can come up with what? 64/58. And this is the weighted mean of, which is what? The price here. This is the weighted mean price. This is the weighted mean price, which is equal 64/58. As you can see, whenever you have several observations, okay, several observations of the same value, then use the weighted mean instead of using the regular arithmetic mean to calculate the average, because this is an easier, faster to do the mean of the data.